Hi, everyone. Thank you so much for joining us today. We'll get started in just a few minutes here. Thank you. Hey, everyone. Thank you so much for joining us for the Impact of Post-Quantum Cryptography on UEFI BIOS webinar as part of the UEFI 2021 Virtual Plug Fest. I'd like to take a moment here to introduce you to our presenters. So we have Jiewen Yao, who is a principal engineer in the Intel Software and Advanced Technology Group. He's been engaged as a firmware developer for over 15 years and is a member of the security sub-team and the TCG PC client sub-working group. We also have Vincent Zimmer, who is a senior principal engineer in the Intel Software and Advanced Technology Group. He has been engaged as a firmware developer for over 25 years and leads the UEFI security sub-team. And I'll go ahead and pass it off to the presenters now.
Hey, thank you. So good morning, everyone. Thanks for attending the session. So what we're going to speak about today is lead off with a background of UEFI cryptography and some of the challenges there, which will then sequence into a discussion of post-quantum cryptography, enabling post-quantum crypto, or what we'll be calling PQC for UEFI style host firmware, and then a summary and call to action in this topic area. So to lead off, I want to just remind folks of the impacts of cryptography in our UEFI style firmware. So cryptography sort of pervades various aspects of UEFI specification. Recall, UEFI is an interface specification between third-party OSs, option ROMs, etc. And as an interface specification, it has some obligations on cryptography. One is policy controls, such as our authenticated variables. In the specification, you'll actually find a specific mention of encryption algorithms like RSA with PKCS 1.5 padding. And in addition, for secure boot, our trust anchors like the platform key or PK, we call out specific RSA key strengths as the recommended. So one of the challenges as the world evolves and threat actors become more sophisticated, computational complexity becomes more evolved. There are insufficiencies in even these two aspects of the UEFI specification. Specifically, the term used in the industry a lot is crypto agility, because a lot of cryptography today, like asymmetric cryptography, is based upon computational complexity. Like RSA is, can you factor large primes? Well, a few years ago, maybe a 1024-bit key was sufficient because it would have taken contemporary computers, 100 years to brute force try to compute those primes. Well, as technology advances, Moore's law, etc., the computational complexity of 1,000-bit key was insufficient. Then it became 2,000-bit keys. As technology continues to evolve, even 2,000-bit keys are challenged, which really made us realize hard coding into the specification, specific key lengths, specific algorithms, does not make for a sort of a flexible standard. So we actually have an open Bugzilla on this topic of where in the UEFI specification we call out cryptography, key lengths, and we want to kind of segregate that, move it out of the specification so we can keep the specification as pure interfaces, data structures, and then track the evolution of cryptographic requirements in a separate area. So this is one activity happening now, and we definitely would join folks on the call and the industry to join in this discussion. So again, crypto agility, let's move crypto responsive to the business ecosystem needs. And it isn't just secure boot, PKs, and authenticated variables. Asymmetric cryptography like RSA is quite pervasive in host firmware. So we have the secure boot use case. We have examples like firmware management protocol capsule update. How do you secure your updates? Some Intel products, features like boot guard, platform firmware resilience, they all call out different crypto requirements. And then other standards like the DNTF and then the IETF or network protocols. So these are additional examples of asymmetric cryptography, whether it be RSA or elliptic curve based, such as ECDSA. So the takeaway from this slide is it's not just RSA and auth variables and PKs we're worried about. Asymmetric cryptography pervades various standards and layers of the stack. In addition to asymmetric cryptography, sort of signing and authenticating that kind of works on small data objects like digital signatures, sort of bulk cryptographic operations that operate on larger, more bulk data, such as hash algorithms, HMAX, etc. Similarly pervade the standards, whether it's our measured boot, where we're extending measurements based on SHA, whether we're hashing our images for secure boot variables, or storage protocols and network protocols. Asymmetric cryptography also pervades the standards. So we have RSA and asymmetric, things like hashing and SHA and AES for symmetric cryptography are sort of pervade the various levels of the stack. And both asymmetric and symmetric have sort of strength of functions on key lengths. So again, as I mentioned, for SHA, there's the pre-image attacks. If you have your SHA is too small, your hash function, folks can guess what your pre-image is. So that's why we don't recommend MD5, because computers you can buy today, desktop computers can probably calculate pre-image attacks on MD5. Even SHA-1 now is being challenged because of that. So folks can calculate pre-images on the hashing. Folks can factor the large primes with RSA. And so cited at the bottom of this slide are some guidance from folks like the NSA on what your strength of these traditional algorithms should be today. SHA-384, RSA 3K, elliptic curves 384. Namely, use these as kind of your minimum, such that if you want to have some resilience against today's classical von Neumann machine doing an RSA prime factoring or pre-image calculation, these are big enough that today's computers will have a hard time. So as you notice, right, some of these are larger than what you saw in the UEFI spec a couple slides ago. That 2048 key obviously is less than 3072. SHA-2, smaller than 384. So this is one of the arguments for having agility and maybe moving forward, namely having more some strength. but are we just worried about classical von Neumann machines, serial machines, breaking, factoring our primes and calculating pre-image attacks? That isn't the only problem on the horizon. The other challenge is quantum computing. So in the mid-90s, Shor and Grover postulated that if you had a quantum computer, you could break RSA, you break SHA, because instead of it, iteratively trying to guess the primes, these large primes that are factors of your keys, quantum computers can explore an entire state space and trivially solve some of these. So, quantum computing at the time was very theoretical. I remember even as an undergrad at Cornell, Grover showing up as the young assistant professor. I think it was prior to his paper here, but this was a while ago, and a lot of these were sort of paper attacks. The world of theoretical computer science is rich with these ideas. So these were ideas in the 90s. And so what would a quantum computer, what would it mean? So we talked about the bit strength earlier of the classical algorithms. So essentially, your asymmetric algorithms would be rendered moot in the world where there's a quantum computer, and even the hash functions, we'd have to move to larger hash functions to have sufficient bit security. So this really puts us in a dilemma. There's an obvious path here with bigger AES and SHA. But what do we do about asymmetric crypto? These are the things that are signing our images, encrypting our secrets for network key exchange. So this is a potential problem if some of these quantum algorithms were realized in practice. And the industry is actually talking about how to frame this problem, specifically with Mosca's theorem. So there's various metrics at the top. For example, how many years will it take to make our encryption secure X, and then how many years to make our IT infrastructure? How many years do I need the encryption to be secure? So X would be if I'm shipping a product, say it's an embedded that has a lifetime of 10 years, or a consumer product, or 5 years, it may need to be secure for the life of the product X. And then Y is how long will it take us to get there? So arguably we're in the Y phase right now. We're working to have crypto agility, have that crypto agility include but be not limited to resilience to post-quantum, to these quantum potential quantum-based computers. So we're in the Y phase now, and then once we get through Y, how long will our products need to live? And the race is Z. How long will it take for there to be a viable quantum computer? So if you look in the press, you'll see Google, IBM, others have quantum computers, Honeywell, but they're sort of small, not deployed at scale yet. So we're sort of in a race between how long will it take for a viable quantum computer to be achieved? Can we shorten the time Y, figure out what we need to do, and then support products that live in that X window? So hopefully this sort of set up the frame of why this is a potential business challenge. And again, working through Y has a lot of technical issues. And so to dive into the technical issues here, I'd like to hand off to Jiewen, who's going to lead us through a discussion of post-quantum cryptography, what it is, and what some of the paths we might take.
Okay, thank you, Vincent. Now I would like to introduce post-quantum crypto and its impact to UEFI based upon our evaluation. Because of the importance of the quantum computing impact, just like Vincent mentioned, the NIST initiated the Post-Quantum Cryptography project in 2016. The goal is to develop the cryptograph system that are secure against both quantum and classic computers and can interpret it with the existing communicating protocols and networks. From the figure below, we can see that the PQC project only focused on the public key-based cryptography. The symmetric key-based cryptography is not impacted, not covered. Currently, the PQC project is in round 3. There are 2 major categories of algorithms. One is the public key encryption and key establishment, and the other is the digital signature. Of elliptic curve, multivariant, and symmetric primitive like hash. We're not interested in the detail of each hard problem in this presentation because they are just mathematics. NIST mentioned that they expect to select at most 1 algorithm for each hard problem. That means among cable, enter, and sable, only 1 of them will be standardized, and between dilithium and the Falcon, and only 1 of them will be standardized. Ideally, NIST will release the draft specification in 2022 or 2023 and finalize the standardize in 2024. Besides the NIST PQC project, the industry is also preparing for the post-quantum. The Open Quantum Safe project is one of them. The first code check-in was in 2016. The goal of OQS is to support the development of and prototyping of the quantum resist cryptography. OQS consists of 2 main lines of work. One is liboqs. You can see the red part on the bottom, which is an open source C library for quantum resist cryptographic algorithms. And the other is liboqs prototype integration into existing protocols and applications. That is the blue part on top. You can see they integrate the liboqs to OpenSSL, OpenSSH, etc. liboqs use MIT license. The implementation is from PQ-Clean project of some direct contribution. liboqs is a C library, and the OQS project includes a set of language boundings to make it usable in other languages, such as Go, Java, .NET, Python, and Rust. liboqs can integrate into existing crypto library, such as OpenSSL, Boring SSL, OpenSSH, etc. In May this year, liboqs announced 0.5 release, which is a big milestone, and the latest release is 0.6. In liboqs 0.6, it almost supports all NIST round 3 algorithms. Both key establishment and digital signature are covered, and the only missing part is GEMSS. And the old liboqs did support some other algorithms. For example, the 0.2 release included a New Hope KEM, MQDSS, and QTester signature, which were round 2 candidate. But since they are no longer in round 3, they are removed from the latest liboqs. In UEFI POC, we did use liboqs, and we will discuss that later. Now let's take a look at the key size of PQC algorithms. This page shows the size of the key established algorithms. The red number means the size is a little bigger. It's bigger than 64 KB, and we need to take care of it. You can also see the biggest one is even larger than 1 megabyte, such as classic MacLease. The next page shows the size of digital signature algorithm, and same as key establishment. Some algorithms the size bigger than 64K, and the biggest one, like a Rainbow, is larger than 1 megabyte. That may bring some impact for our enabling work in the future. We'll discuss that later. At the current point of time, we can think the industry is in transition. On one hand, we still want to use the current modern cryptography and get the FIPS 140 certificate. On the other hand, we want to consider the new PQC algorithms to resist the post-quantum, to resist the quantum computing attack. In order to avoid giving a simple A or B answer, NIST allows the hybrid mode. That is the current BKM, that if a production can combine a PQC algorithm together with the NIST-approved algorithm to still receive the FIPS validation. For example, we can combine the PQC key establishment algorithm with EDKII to perform key exchange in TLS 1.3. We can combine the PQC digital signature with ECDSA to do some authentication work in TLS 1.3. And we can issue a X59 certificate with both PQC signature algorithm and with an RSA. With hybrid mode, the attacker need to break both current modern cryptography and PQC at the same time. That is a hard task. Besides the hybrid mode, another transition plan is to use the stateful hash-based signature. The short name is HBS. We call it stateful because the HBS private key consists of a large set of one-time signature private key. The signer need to manage the state of the keys to ensure that each one-time key can only sign one message. If attacker can obtain the digital signature for two different messages that were created use the same one-time key, that would become possible for the attacker to forge the signatures for arbitrary messages. Therefore, when a stateful HBS scheme is implemented, extremely care need to be taken in order to ensure that no one-time key is ever reused. With stateful HBS, one specification for one specific public-private key pair, the number of signed message is limited, so it cannot be used for a general purpose digital signature. One special usage for HBS is a firmware image authentication because we need to sign the firmware image with limited time. Currently, NIST already approved two stateful HBS algorithms. One is RFC 8391, that is XMSS, and the other is RFC 8554, that is LMS. The XMSS and LMS are quite similar. Both of them contain the one-time signing key and a hash tree. The crypto want to use we mentioned that the HBS only support the sign a limited number of messages given one specific public-private key pair. The signature number depends upon its parameter h, which represents the height of the hash tree. For example, when h is 10, then the key can sign 1,000 messages. Assuming we need to sign a release image every day, that the key can be used for 3 years. But if a developer wants to sign multiple debug images for debug purpose, assuming we have a project 100 developers working on it, and every developer needs to sign 10 images every day. That means we need to sign 1,000 images in one day. Then we can choose a bigger H number, like 20, which can be used to sign 1 million images. The public key size is irrelevant to the parameter H. Only the signature size is related to H. The more signed message is required, the bigger number H is needed, and the bigger signature size is. There are also reference implementation for hash-based signature. For example, Cisco provides the reference code for MAS in C and Python. And for XMSS also has a reference in C and Python. A good news is that OpenSSH integrated XMSS support, but it is experimental only and disabled by default. We will discuss the UEFI POC for MS and XMSS as well. In next section, I will discuss how we enable the PQC for the UEFI BIOS. So first, let's look at the potential PQC usage in UEFI. We consider two categories. One is the general purpose PQC algorithm. For example, the key establishment is needed for TLS session or SPDM session creation. The general digital signature can be used for runtime challenge and response, such as identity authentication for TLS or SPDM. The other usage is a stateful hash-based signature used in special use case, such as secure boot, capsule update, signed recovery. The secure boot image verification and the variable authentication happens in UEFI phase, and the capsule update may happen in EDKII or SMM phase. And of course, the signed recovery may happen in PR phase. And we can enable all of them by using a stateful hash-based signature. To cover the general PQC usage, we built liboqs in EDKII. We think liboqs is a good library. It defines a set of common interface for all round 3 algorithms. For example, OQS signature new is for all digital signature algorithm. OQS KEM new is for all key establishment algorithm. If later a program needs to switch to a new algorithm, it just needs to change the algorithm name. The OQS has traditional crypto dependency, such as AES, SHA, and RAND. liboqs includes its own implementation and allow user to link OpenSSL function as alternatives. liboqs considers CPU and the specific acceleration. For example, it may use SSE AVX on x86 platform and use ARM, SHA, or AES instructions directly. However, we also encounter some challenge during the enabling. The first challenge is build. liboqs uses CMaker, while the EDKII uses RNF. We need to write RNF file for each algorithm. The second challenge is compiler dependency. For example, Bike implementation uses GCC specific functions and only works in a GCC environment. And HQC implementation caused the check stack link error with MSVC. We haven't enabled the special CPU instruction-based acceleration, such as AVX or AVX2 in UEFI, which may bring performance impact. The last but not least important, some implementation use a large stack up to 4 MB, which cause stack overflow to heap area in UEFI, and we may got some free pool, weird memory allocation failure or free pool failure. We can discuss that in the next page. So first, we know that some BIOS code is executed in the resource-constrained environment. And this table shows the typical size of stack and heap in each phase. We can see we do have limitations. UEFI Spec requires the minimum stack size is 128K. The EDKII follows this rule and just set the stack size to be 128K. In PEI phase, the memory is quite limited. Before the DRAM is ready, the EDKII set up stack and heap in cache temporary memory. For example, the OBMF leaves 64K as cache. For real hardware, the number depends upon the CPU L1 cache size or SRAM size. It might be a little bigger, such as 512K, but it won't be too big. After the DRAM is initialized, the PI core will migrate the content from cache or SRAM to DRAM and assign a bigger memory. For example, the OBMF allocates 300 megabytes for PI. The stack size for PI is also limited. Usually, it is half of the total temporary memory, and it is 128K as maximum. SMM is another resource-constrained environment. Today, a typical platform has 8 megabyte SMRAM because the stack cannot be shared for different CPU. The CPU SMN driver allocates stack for each processor. The EDKII allocate 8K stack for each CPU by default, with the assumption that SMM code will not consume too much stack. However, if we enable some cryptography, we do need a larger stack. For example, some real platform override this default value to 64K or 128K. In order to detect how many stack or heap are used in different PQC algorithm implementation, we enable the stack usage calculation. The idea is that before the code runs, we mark stack with some fixed pattern, such as 5A, 5A. After the code runs, we check the content of the stack again to see if the pattern is still there or it is corrupted by the algorithm. We tested with MSVC on x64 build. We can see that classic MacList requires a bigger stack. The biggest one is 4 megabyte. The heap is also requires some more than 1 megabyte heap there. Frodo KEM and site compress also consume larger stack, which is bigger than 128K default value. And here is the result for the digital signature algorithm. Because the general purpose signature, we cover the key generation, signing, and the verification. We can see that the Rainbow requires a big stack. Rainbow 5 is close to 4 megabyte. Dilithium also requires a big stack, which is close to 128K. Besides liboqs, we enable 2 stateful hash-based signature algorithms, that is LMS and XMSS. Unlike the general signature algorithm, we only need a verification function in EDKII because the key generation and signing happens in the manufacture phase. For secure boot or for secure boot or signed capsule update. Enable HBS is also challenge work. We need to create INF for those libraries in EDKII. Second, the MS and XMS API are not consistent. We noticed that XMS reference code just use one API to verify the signature, but LMS hash signature do not assume that fit all messages in memory, so it provides a set of functions like signature init, signature update, or signature finalize. With those three functions, they can finish a signature verification. Third, the compiler dependency. The XMS reference code uses a variable length array, VLA, which was allowed in C99 standard. However, it is not supported in MSVC. In order to make the code work in a Windows environment, we have to change the variable length array to a maximum sized fixed array, which may cause some big memory in stack. The last is execution environment. XMSS reference code use the dvurand to get a random number. In order to make it work in UEFI, we need to implement another random number function. We also calculate the stack heap size for both reference code for LMS and XMSS. From this picture, we can see it is quite acceptable. XMSS consumes a little bit larger stack than LMS, which is reasonable because we change all the implementation use the maximum size to replace the variable size array. If we can use a smaller parameter, we can definitely make the stack smaller. All those POC code can be found in GitHub repository, include liboqs, LMS, hash signature, XMS reference integration to EDKII. Please note that it's for research purpose, but please don't use that for any production. Besides our work, Cisco people published a paper, the Post-Quantum LMS and the Spec hash-based signature for UEFI secure boot, and describe the performance data, and that matches our observation too. For hash-based signature, the key generation is very time-consuming. For example, if we use XMSS with a height value 16 or 20, the key generation will take several minutes. Fortunately, the verification is very fast. They also say that now the proposed parameter set perform verification slower than 7 milliseconds, which is quite satisfactory. Besides the memory size, we can see the challenge on the PQC enabling in general. For example, the UEFI spec requires a PKS7 signed data, such as p-image, capsule, and Auth variable. We need to integrate the existing PQC algorithm to PKS7 with a new OID, object ID. Otherwise, we can only use the raw signature data, which is not preferred. For X509 certificate, it needs to include the public key and the signature. And the size might be a problem because from previous page, we can see the size might be bigger than 64K. And key exchange data in a secure session handshake phase also include the public key and exchange the cipher text. And the size might also be bigger than 64K. In UEFI API spec or EDKII implementation, some data structure does have some size limitation. Take UEFI variable as an example. Windows requires that individual UEFI Auth variable size is 64K as minimal, and EDKII set that value as default. The variable storage size has also size limitation. For example, the EDKII defines a 128K as default, and OEM platform overrides it to 256K. And according to PI spec, the hop length is a uint16 field. If we need to store data bigger than 64K, we need some special handling. In flash file system, the file and the file section also has some size limitation. That is 16 megabyte for version 1 and we move to version 2 if that is we need more for that. Beyond the UEFI, the other industry standards also impacted. For example, the BIOS may enable HTTPS boot, and that requires a network TLS. The TLS include the public certificate, digital signature, key exchange data, include public key and ciphertext. And the researchers published paper that prototyping post-quantum and hybrid key exchange authentication TLS to describe the detailed analysis. The prototype is available, which does support hybrid mode. Besides TLS, the BIOS may use SPDM protocol to authenticate the device and get the signed measurement from the device, or create a secure session to communicate with the device. The SPDM is very similar to TLS. It includes some public key certificate, digital signature, key exchange data, etc. SPDM also includes a command named getCertificate, and the length offset field is 16 bytes. That means a certificate chain cannot be bigger than 64K. If it includes a PQC algorithm larger, then that command cannot be used. We need some improvement for this command. Also, the SPDM secure session uses the UE16 length, which means a session message cannot be bigger than 64K. For the hardware transport layer, SPDM can be on top of the PCI DOE mailbox. The maximum length in DOE mailbox is 1 megabyte. However, we do see from the previous page that the sum signature and key exchange data is even bigger than 1 megabyte. In order to support that, we prototyped a PQC version SPDM with fragmentation support. The algorithm is based upon liboqs, and we support hybrid mode, and we can transport large SPDM messages with a customized fragmentation that can make sure the SPDM protocol can still be used in the PQC world. The future TPM is another research project on post-quantum cryptography. Researchers did analysis and prototyped and noticed the limitation. For example, the default I/O buffer size is 4K, which is not big enough, obviously. The stateful HBSK generation time is much longer than the default time. We notice the key generation time is based upon the height of the tree H. If H is 20, it will take several minutes to generate the keys. In order to maintain the state of the HBS, we need a larger TPM ME-RAM, and the current size might not be enough to store the whole private key and its state. And the same issue on the internal cache. We need to store some XMS as cache data for optimization. Here is a summary for our talk. So first, we're observing that the industry is preparing for the post-quantum cryptography. Second, for UEFI, we are preparing for PQC and consider the crypto Agile design with the hybrid mode. We filed the Bugzilla on this crypto Agile. If you have any feedback, feel free to comment there. Third, we should consider the PQC implementation in a resource-constrained environment, especially for the BIOS use case. There's the stack size and heap size are quite limited. Okay, that is all for our day's presentation. I will pause here to see if there's any questions.
Great, thank you. The first question here is, why not stick to heap allocations where possible over the stack? Is performance really that significant?
Why not stick to heap? Why not stick to heap when possible to overstack? I think that's just the implementation choice. If I would say, if I did look at some liboqs code, they just put some parameter to the stack. And I think it's also possible to allocate heap in the entry of the function, use it, and free it later. I don't think there's any implementation issue, but I do think this might be some performance impact because heap allocation has much impact than a stack. So I treat it as an implementation choice. And another way is we just the implementation can allocate a big heap in the beginning and just use that data in this heap to avoid the frequent allocate free, etc.
Great. We'll give it one more moment to see if we have any additional questions for the Bright Talks Q&A, and then we can go ahead and switch on over to the live WebEx discussion. All right. Well, with that, oh, sorry, we have one more question here. So the next question here is, given the NIST approvals are expected in 2024, when do you expect PQC implementations to be adopted into the UEFI EDKII reference?
That depends upon if we have some business need on adding this PQC algorithm there. For example, after we see it is NIST as approved algorithm, if OpenSSL adopted it, and the liboqs implementation adopted by OpenSSL, and we also see some customer want to use that in their BIOS reference code, we can definitely add those features in EDKII. So it's based upon the maturity of the implementation and the business need. So, Vincent, do you have any thought on that?
Yeah, I think it's more responsive to the business need, and perhaps some folks will be a little more aggressive. For example, the capsule update use case. So the capsule update the digital signature mechanism isn't really dictated by the standard. The capsule is kind of just the transport. So perhaps if when we talked about that Moreno's theorem or equation earlier about kind of trying to Oscar's theorem, excuse me, worried about making the readiness time shorter because of a long product lifetime. I could see some folks perhaps even adopting some of these algorithms pre-NIST for a product. But in general, yeah, I think we prefer to have NIST approved, third-party crypto community supported. One of the reasons we chose OpenSSL a decade ago was the admonition against writing your own crypto. So yeah, I agree with you, Jiewen. A lot of this will be responsive to the business need.
Yeah, and I would also say if we do see the business need maybe before NIST, like you mentioned, we can probably add some implementation to the EDKII staging tree to allow people to pre-test those implementations, something, so people can get better prepared on this PQC work.
Yeah, no, I agree. Or if people want to do risk execution of using staging in product, since it's a community project, can't dictate how people use the code. But yeah, I think staging is a great way we can incubate and get readiness, because last thing you want is when the standard drops from NIST to suddenly start your R&D readiness, right? Given the long timeline of software development projects with this type of infrastructure.
All right, well, with that, that was actually our last question. So we'll go ahead and move on over to the WebEx Q&A. So this will be an opportunity for you to chat live with the presenters, and it's meant to be more of an open dialogue discussion. We did go ahead, we're displaying this via the chat as well as on screen. And then just as a note here, these slides and this recording will be available after this webinar concludes. So thank you, Vincent, and thank you, Jiewen, for presenting, and thank you, everyone, for joining.
Hey, thanks, everyone.
Okay, thank you. Thank you, Mike.